Cool. Okay. Yeah. Give me a second, guys. Yeah. Mm. Can you guys see my screen?
Yes,
Okay, cool. Since I, kind of restarted on this topic, so I'll just, give a quick refresher. Basically, how MapReduce works in our context is that when we take a normal program, it runs on a single machine, and it runs maybe on single or multi-threaded fashion, where we are loading the data and the program from the disk or hard drive here, and then loading it into a RAM, and our program will be sent to CPU and it will be decoded as instructions, and these instructions will again load the data from RAM into CPU, process them, and provide the output to the RAM, and then eventually to disk. So this is how single node machines work. This is how data processing works on a normal scale. But not but yeah, this is how normal this one work. This is a fantastic example how by and large how databases works, or normal single node databases work even to this day, be it on cloud, be it on prem, it doesn't matter, right? So we use, like, for these kind of processing data, either we use programs like are written in C++. These are basically called as imperative programmings, and we are doing it on a single node. We can also use something like SQL, which is a declarative programming language where you will just provide statements like select star from db dot table, and then the database on this server on a single node will uh, likely decode what is this statement, and it will give us the results based on that, right? So why do we need, like, much more larger processing, albeit a distributed processing, for that matter? Because we established a fact with our HDFS sessions that the the data itself is not storable, or like exceeds the storage of single machine. And with that being said, we don't have a way to, like, process them on a single machine, because it's the data itself is spread across multiple machines. We discussed at length how data is stored, scaled, and failure methods, all of that in HDFS. You can refer the earlier videos. But yeah, once it is done, storing, how would we process it? So that's where this distributed processing comes into picture. To achieve that, there has to have a new standard of processing data, right? Because traditional systems doesn't work. You cannot just go on multiple machines and say that, okay, run this program, and coordinate between them based on what happened, whether the data is processed successfully or not, right? This is not how it should work, because it takes a lot of energy and coordination between teams to achieve it, and which is not generally a good case, right? When we are doing when you're processing data that is much bigger than single machine's capability of storing and processing data. So how do we do that? So that's where MapReduce as a programming paradigm came into picture, where when we did store data as blocks across multiple machines, and we kind of said that, okay, if the data has to be processed, we can locally process on these nodes, right? So that's how the origins of distributed storage happened. And bolting on top of that storage, we are creating a new paradigm of processing data, that is MapReduce, which is basically a programming paradigm, right? It's not a simple different program that is written for distributed environment is a different program, a programming paradigm. What do I mean by that? Before we just jump onto it, we will understand what is map and what is reduce, right? What is a map? Map is basically, if you check the example here, basically we have list of numbers. Okay, we want to apply one single function here, that is square of a number, right? We want to get square of a number. Okay, so what are we doing here is basically we are trying to take a number as an input, and we are trying to square it and give the result back. Okay, I see I've raised a hand. Anybody raised a hand? No, right? I think it's the gestures that is picking up. Okay, that's fine. Anyone has any doubt? No, right? Cool. Okay. So this is what we want to do. We want to apply a single function. Here lambda is basically an anonymous function. Okay, which doesn't have a name, but it has a function body, right? So what we are basically doing here is we are providing a function onto a list of elements, and we want to apply the same function across all of these elements and get the data out of it, get the result out of it. So this is basically a map. A reduce is basically reducing the list of values to a single value. Let's say I want to have a greatest value out of all of this, right? So only there can only be one greatest value, right? So that's how the reduce function work. Reduce basically aggregates uh, values and provides the output. Let's see an example here, right? So when you are seeing going through this example, right? As I've explained earlier, this is a lambda function, this is an anonymous function, and we can write in a normal way or normal function in we can expand this function into a normal function like this, right? It takes a value, it has a function name called square, and then it returns n square value, right? Same thing here, it takes one output, one input, it outputs square of the value, and this function is basically applied to all the numbers, all the values in numbers list, right? So this is how map works. Okay, and how reduce works, right? Again, we are taking a list of values, and we are saying that we are again taking two values here as inputs and checking if x is greater than y, right? And then based on that, we are picking the final value. That's it. So if we expand the function here, the anonymous lambda function here, this is how we would see it. So all of these functions here, the square function, the max function, right? These are all deterministic function. That means when you give the same input, it will give us the same output. So this is what basically MapReduce is built on top of. We have deterministic functions, right, that are at the heart and center in of MapReduce. And based on that, what we are doing here is we are calculating values out of it, and we are doing it. And this is happening across all the nodes in the cluster, right? Deterministic functions being executed across all the clusters on all the blocks at once, and then getting the output out of it, right? This is how MapReduce is. We have already seen some aspects of MapReduce, like properties of MapReduce. It is a distributed system, and it runs it has massively parallel execution. It can scale horizontally. That means that if you have for like two node cluster, Hadoop cluster, right? This is your name node and this is your data node, right? Suppose I have a lot of data incoming, I can just add another two nodes here and then scale it, right? These two nodes again can increase the compute as well. We can increase the compute on these systems as well. As soon as we add um, the nodes here, we also get boost in compute as well, right? So this is called as horizontal scaling. We are increasing the nodes. That's why we are calling this as horizontal scaling, right? Built-in fault tolerance. Basically, if any job fails here, it can be retried again and again until it reaches maximum, runs or maximum failures or a pass result. So that's what this is basically. And we have also discussed about what is functional programming, how we are using this. All right. So now we also discussed about stages in MapReduce. I'll not repeat it, but I'll just explain it on the surface now. Right? What is in we have certain stages in MapReduce when we are handling it in distributed manner, right? On a Hadoop cluster, as you are seeing it here. So when we are like when we have written a certain logic, let's say word count problem, right? A popular simple like program where you have asked in your particular machine you have written this in a Java program that achieves word count of a particular uh, source data on a particular source data. So this particular Java function or Java application will be converted into a jar file, and it will this client on which we are writing the data, on which we have program, will ask the name node, where do we have this data? This name node is basically your HDFS name node. Where is my data? It provides that particular information to the client node. The client will send the data, sorry, the program to each of the nodes where data is present, right? So why does this do that? So this is the new computing paradigm that we are talking about, right? Earlier we had only one system where it had RAM, CPU, storage, hard drive or SSDs on one system, right? So the program, the data, everything is stored was stored here. But if you think about it, right? If the data is too large to be stored and cannot be stored on single system like this, we had to distribute it, and we did distribute it through HDFS. Now, if you want to run, processing on these particular aspects of the data, we have to literally send the program towards the data rather than data towards the program, right? Which is what we are doing here. And once we do that, the program will be running locally on the data on the nodes where the data is stored in the Hadoop cluster, right? This is called data locality, and HDFS, sorry, Hadoop MapReduce will be its default behavior is that wherever the data is present in the node across the cluster, it will be sending the program towards that, right? What does it do after sending the program? The first stage is input splitting. That means in the blocks of 128 MB data we store, it will start to read the data as soon as it gets the files, right? Input locations. Let's say the location is like data slash data slash raw slash books. Okay, some location like this. Your HDFS program, sorry, MapReduce program will like read the data from this particular location, starts splitting the data into records, right? That is how it is. Every block will have one map phase, right? So this is how input splitting happens. In this particular 128 MB block, we will have n number of lines here. So each line will be split into one single record. Okay. Each line is one record here. Okay. Any doubt? Okay, cool. So the next step is map phase. So once the data is read, it's on your RAM locally on this particular data nodes. So what do we do that? As we have seen here earlier, right? We want to apply some function, right? We want to apply some function here. Okay. Give me a second, guys. Can you guys hear me?
Yes.
Okay, I think my laptop got stuck for a minute. Yeah. Okay, cool. No issues. Hmm. So as soon as we have read the data, right, and we want to process the data, that means in the map phase, as we had discussed earlier, we have some function to apply to all of these records, of data that is split in blocks in HDFS, right? So what we are going to do is we will, since we have already read the data in input splitting, we will start reading the data and apply. Sorry, we will start applying a function to the data. What is a function here? A function is basically something like this. Okay, function is basically something like, okay, what's happening? Give me a second. Yeah, a function is basically like your squared function. Okay, in the context of MapReduce, right? In the context of word count, here the function would be to split the data, which is your sentences. Okay, in word count example, okay, this function would be something like this: split sentences, okay, sentences into words, okay, into words. So this would be your function. This would be your function for the word count example. Okay. So that is how it works, right? So for example, let's say we have this one, a string called hello world, right? This is your input sentence. The mapper output would be hello comma one and world comma one. That is how it works. When we are mapping, we are saying that, okay, this is an example function here. As you can see, what we are basically saying that, okay, map, take my string as key and there is a value here, right? So for every word in the value, which is this particular hello world sentence, we are splitting it. And okay, we are doing a split here. And for every word, we are saying that, okay, word comma one. This is my map. So this is how mapping would happen for the input, where we are extracting the data in plain text from the block files, and we are converting this into a mapper output, which is basically saying that, okay, I want to count all of the words. So let me just read the words, read the sentences, convert them into words, and then just assign them count as one for each of them. So this is basically your count. Okay, this is not the final count, by the way, or the final output. This is just an intermediate output. Every map's output is an intermediate output, right? So once we have done that, we will have many repeating instances of hello. If the file that we are reading has hello a lot of times, it will have hello one, hello one, hello one, hello one, many times, like n number of times. So what happens here is that since this is in single working node, the output that we are seeing here, that for the mapper is on single node. If we have like n multiple nodes on the cluster, we'll have different like outputs for each of these particular nodes, right, and none of them are like aggregated. That means that we don't know the exact count of on how many times the word hello has occurred yet, because like the input splitting, the count, all of them are done at each individual machine's level within the cluster, and no one node knows what the other node is doing at any point in time, right? So we don't know what we are doing here, right? So how do we know what is the final count of the words are in our particular input, right? So for that we have something called a shuffle phase. What shuffle phase does is, okay, if you have n number of n occurrences of each word, right? which is basically saying that, word comma, okay, word comma 1. Okay, and then like likewise for n number of words, okay, word 1 comma 1, word n comma 1, like that. So this is the output of the first mapper phase. So if you want to know the final count of what exactly how many times the word 1 comes out, right, we have to like get it to one single machine, right? Unless we do that, we don't know, like, because the data is split across multiple nodes or multiple machines on a single node, and we don't know, like, these nodes will not have internode communication, and the only communication that these can have is to shuffle the data, right? Shuffle the data, that means once we are done with calculating our map phase, the output, we can send it to another machine and say that, okay, this is my output, and you have your output, so you can just calculate one single output out of both of us, right? So to do that, we need shuffle phase. Shuffle phase is basically where you collect all the intermediate keys and then group them. Okay. So for example, if you have n number of like hello occurrences, each of them have count one, and finally after the shuffle and sort, basically you will get the output like this. So it shuffle and sort, basically what they does is, first they will sort according to the key. Okay, sort as per key. Basically key is your word. Okay, in word count example. Okay, and then shuffle basically means copy onto a remote machine. Okay, copy onto a remote machine. Okay, so now, since we have already sorted this data, and we have collected all the counts of occurrences of hello, we can send it to one single machine, that is your reducer. It can be 1,000 count once, 10,000 once, it doesn't matter, right? So the next phase is your reduce phase. Reduce phase is basically saying, okay, I have got a key and I have got a value. The value is basically like a list of ones, and I will just, if I just add them, I'll get the final count. So the output of your reduce phase is the final output. Okay. Again, if you think about it, right? Uh, the input splitting is handled by the framework, right? That means your framework, MapReduce framework, will read the data from the blocks, and then it will convert it into key value pairs, right? And the value here is the sentences, and the key is just a random generated key, or the just the file offset of that particular row or particular record, right? In the map phase, what happens is we are taking the value of the input split, and we have to write the logic. As a user, we have to write the logic as to how do I handle that. So we said that, okay, we want to split the sentences into words, and then assign them each word as count one, excuse, as count one. Okay. So the shuffle phase is again handled by your framework. Okay. We don't have to do anything with the shuffle phase, right? And finally, the reduce phase. Reduce phase is how the user wants to see the data at the end, right? So we are defining that as well, right? So reduce takes the input, reduce tasks or reduce phase takes the input from your shuffle phase. Once the data is sorted, and if you take a cluster of four nodes, right? Four nodes. Okay, three of them would be processing the data. Okay, these are map, like these are processing data with the help of map. Okay, and one node will act as a reducer. Okay, by default, your reducer will be one node. Okay, by default, and your mapper equal to number of is equal to number of blocks in your Hadoop cluster. Okay, number of blocks for the file. Okay, so what do I mean by that? Let's say you have a 500 MB file. Okay. It will have four blocks of three blocks of 128 MB. Okay. Three blocks of 128 MB plus one block of 116 MB or 112 MB, something like that. Right. So ultimately, we will have four blocks that contains the 500 MB. Now, when your MapReduce program starts, it will have four mappers here, okay, to process all the blocks, okay, to process all the blocks, and one reducer, okay, four mappers spread across three machines, right? How does this work? So the first time when the MapReduce program starts, it will assign three mappers here: mapper one, mapper two, mapper three, and then let's say mapper one finishes the task first. Again, mapper four task will be assigned to mapper one. Since the data is spread across all the nodes, we can just get the data from here. So all of the processing of the data from these nodes from the map phase will be sent to one node, that is your reduce phase. Okay, that is your reduce node. So that is how it works, right? Since we have one single node as your reduce, the output, the number of files it outputs is one file, single output file. Okay, so that is how this works. Okay, you can have multiple reducer nodes, by the way, but then you need to write a way, your program that it consistently provides or splits the data from map phases into the multiple ways so that each reduce node will get same amount of data, right? Let's say we are doing map reduce for word count, right? So I'll have something like this: my input from my map phase, whatever the word, if it falls under A to M, that will go to reducer 1. If it falls to N to Z, it will go to reducer 2. So my output will be two files in the final HDFS location. Okay. So this is how it will work. Okay. Any doubts? Cool. Okay. So the next step is these, like these different phases here for the MapReduce job, which is read from file, map the file for input, and then write to disk. This is an intermediate step. And then finally, we are doing a shuffle and sort of the map output and then writing the disk to data. Again, read the data from, like from the disk and then, finally reduce and then write the final output to disk. So the intermediate data that is generated by any map or shuffle and sort will be written to disks of the data nodes that is independent of the Hadoop file system. Okay. And when the next phase starts, the data is directly read from these disks. So how record reader works, we have already seen that. Okay. So how input splits, this also we have seen. Let me not repeat it. So yeah. Now coming to the map phase, right? Again, I'll just repeat a bit. So here, when we talk about mapper phase, right? We have to understand that this is the workhorse of the whole MapReduce setup. What do we mean by that? That this means that anytime you want to do a parallel processing or any sort of processing that is happening across your nodes, you have to use a map phase. You have to use a mapper function so that it can run parallelly. So the most of the heavy lifting that we do with the MapReduce phase will be done directly through mapper phase, right? Only phase can run effectively parallelly and crunch a lot of data very effectively, right? It's not the reducer phase or any other phase, but yeah, map phase, right? So the primary goal of any mapper phase is to just process the raw data and get the data into some shape so that the reducer phase can provide the final output of the data, right? So how does this work, right? As we have seen in our Hadoop cluster, when we have data lying on different nodes, what we are basically saying is that, okay, I am the client, I have written up my program, my produce program, I'm asking some metadata about the files. I'm sending a request to my name node on the cluster and saying that, okay, I want to process this data, and I'm asking for locations of this data from name node. It will send me the data of the locations of the files, and I'll directly dump my program to each of these nodes here. So this is effectively like saying that, okay, data node, take this particular program here and then run it. Okay, like that. So this running of program directly on this one, directly on this node, is called as data locality. Okay, data locality. Right. This is really important. This whole idea of data locality is very important, because unless we are processing the data locally, even though we are saving the data across multiple nodes, it doesn't matter, right? If you think about it, because we are not doing any parallel processing, even though the data is spread across multiple machines, right? We are just leaving a lot of processing on the table. We are just consuming a lot of time to get the data. Since we have data locality on, and Hadoop MapReduce naturally adapts to it, and executes the data parallelly very naturally, so we are benefiting from that, right? So how it happens is that whenever we are providing the like program to this particular nodes in the cluster, the first thing that MapReduce does is try to optimize the network bandwidth. What do I mean by that? So we have discussed that MapReduce, there is a lot of shuffle involved, there is a lot of writing disks involved, all of that, right, in the previous sections. So basically, what that means is that if, let's say, due to resiliency and all of that aspects, as we discussed in HDFS, if two nodes are present in one rack, and two nodes on my cluster is present in another rack, I'll try to provision my MapReduce job on these two nodes as closely as possible. Even if there is a shuffle, I can just easily shuffle the data between the nodes or within this particular rack. Okay, this is the first thing that it does, the Hadoop MapReduce framework. Whether I have the data within the rack, yes. If then yes, I'll start my program here. If it is spread across this one, okay, within the same network first. Okay, if it is closer to my rack, or if the nodes are closer to the racks within each other, yes. If they if not, whether they are present in the same physical location or not, yes. So it has some hierarchy, right? So same network, okay, same network is always better than same rack, okay, which is always better than same region. So this is the hierarchy of how MapReduce job is getting provisioned, right? Is getting provisioned and executed, right? So how does this work? So this is your user program. This is your golden copy. Basically, this fourth means a golden copy of your program. This is basically a jar file. Okay. Golden copy means basically we are not editing in the font. There is no editing that is happening on any of these files. You are just giving the program and it is just executing the it on the data. That's about it. Right. This is a jar file written in Java. Okay. This is a jar file that is written in Java. So basically what it does is fork basically means, it's a golden, copy. And then we are just, forking it and, copying that particular program or that application directly into a worker node. Okay, through master basically means your name node here, right? And then when the worker reads the data from the input splits, that we already know this is derived from the data that is stored as blocks, physical blocks on the Hadoop HDFS cluster. So we will read the data from the input splits, and we will start them like processing them on worker nodes, which is our data nodes. And then once we have done processing successfully, we will do a local write on these worker nodes, right? So the reduce phase, which is this phase, right? This particular phase will do a remote read. That means it will go to these particular worker nodes that have done already done processing the data, right? So they will store the data on disk locally within those nodes. So what this reduce phase does is it will go to that particular node and read the data and start, working on the reduce operation, right? Finally, we will have a number of, files for a number of reducers. So this is how it will work. So I'm repeating again and again so that we all are on the same page and we are not getting confused. So here, none of the workers, be it on the map phase, okay, be it on the reduce phase, they don't have any idea about anything that is happening on the other nodes or other phases. So this is called as stateless execution. This is very important since we have deterministic functions and it follows functional programming paradigm where we say that okay, for the same input we are getting the same output, which and that is called as a deterministic function. So basically what we are doing is, yes, we are trying to like run this as a stateless entities or stateless programs across these nodes. So that's how it works, right? So we have discussed reduce phase and yeah, final aggregation. Yeah. Okay. So the final output of any reduce looks something like this, right? The okay, Apple. Let's say we have 10,000 occurrences of Apple, so that means the output will be Apple dot 10,000, Apple comma 10,000. Okay, and we have something like any, right? Okay, this will have, and let's say 500 occurrences. Okay, so on and so forth, we will have output of all the words and their final output counts present here in the output of reduce file. Okay, now since we discussed about map, and we said that okay, map is highly parallel and all of that, how does reduce work? Reduce is not parallel by default. We could make it parallel, but then we have to provide a particular hash function. As I've told, right, in word count example, our hash function is a to m in one reduce and n to z in another reduce, right? So this is a logic of splitting the output of mapper phase, okay, output of map phase into two parts so that each reducer can have one chunk of the input from the map phase. So that's how it is. So that is why we are seeing what we are seeing here. So by default, any Hadoop cluster, when we are running a program, any MapReduce application will have only one reducer. Okay, only one reducer. There is a drawback to it. I'll discuss it in a bit, but we will have only one single reducer in by default for a MapReduce application. We can change it and we can provide the number of reducers in our program as well. Right. So this is how reducer work. Reduce is fundamentally not parallel, but yeah, we can like provide some way where we can say that okay, my final output can be split across these two nodes so that I can get the data aggregated. Right. Okay, as I've discussed, right, two input files, totaling of 1 GB, that is 1024 MB. We are just doing a napkin math here. Napkin math is basically like, given a scenario, how would, this whole thing look, right? So here, if you have, two input files for our MapReduce program, let's say, have, both of them are totaling around, 1 GB of data, right? So what we are doing here is that we know for a fact that on HDFS these the total of 1 GB is split in terms of 128 MB files, 128 MB blocks, right? Because this is the default block size. And finally, it means 8 mappers, right? 128, 1024 MB divided by 128, which is 8 mappers. So we need 8 mappers to process two input files, which has 1 GB of data, which are, combined 1 GB of data, right? Number of default reducers is one, but this could be a bottleneck, but we can increase it, and we can like do input splitting, and we have to give a custom logic to how to split the data across reducers, right? So what if we just arbitrarily increase the number of reducers rather than one? Let's say, if you know I'll increase the data to sorry, a reducer count to 10. What happens here? What happens here is basically, even though the data itself in the final 10 output files, these 10 reducers, output is 10 files, right? 10 files, right? Even though the data is not necessarily 128 MB here, the Hadoop cluster will create 10 files. Sorry, the MapReduce program will create 10 files on the Hadoop HDFS cluster. So if the data is not 128 MB, but we are still storing them as separate files, it will create a problem called small file problem. Okay, what is this? So each of these 10 files should will have one metadata. Each will have one metadata entry. That means 10 metadata entries for our metadata. Okay, metadata entries in HDFS. Okay, in HDFS, right? In HDFS. That means we are unnecessarily increasing the number of output files, which are not like fully 128 MB per block, and then we are like creating a lot of metadata entries, which will ultimately mean that anytime some job is dependent on these files, it will have to like read more data from name node, and create more instances of the tasks, and it will just create a lot of bottlenecks down the line. If this just one job is, instead of creating one file, it is creating 10 files, imagine the hundreds of thousands, or if not millions of files that are going to be created. And it is just increasing the metadata entries, because as we discussed, the metadata entries on the HDFS cluster, right? The metadata entries on the HDFS cluster should fit in the memory of this name node, right? It should fit in the memory or RAM of the name node. Okay, memory of name node, right? So when we have, instead of one, file, we have 10 metadata entries for the same amount of data. We are just increasing the records on the RAM of this name node, which is not a good case, right? So that's why we need to avoid. We will not know directly to how many nodes, reducer nodes we need. It can be a little bit of trial and error, but it's better to, if the data is like truly massive, like terabytes and terabytes of data, or even gigabytes of data, right? We will use 4 to 5 like nodes, as reducers, and then we can process the data accordingly, right? So this is one good way to like think about it. This, give me a second. Okay, so there is one scenario that I want to discuss right now, right? I'll take back to the shuffle and sort phase. Give me a second, guys. Yeah. So before reduce phase, right? In shuffle and sort phase, we are saying that we are sorting the data by key, and we are providing this data to reducers, right? Can you spot a can you spot a potential problem here? Anyone? I'll explain what we are doing. We are sending a key along with the list here, along with the list of ones, just ones. Okay. If you have 10,000 entries here, we will have 10,000 ones. Okay. If you have 5,000 entries here, we have 5,000. If we have, 100,000 entries for Gemini, occurrences of Gemini, we'll have 100,000, like ones here as a list of ones. So do you see any problem here? Anyone? Okay. So the potential problem here is that we are just repeating values, right? And sending list across nodes for potentially million lot of words, like hundreds of thousands of words, would be a lot of data, lot of network bandwidth, just consumed, and we are just not even sending the actual counts. We are just sending list of counts. What we can do is we can improvise this better. How do we do that? So ultimately, what reducer does is, we as reducer, it will basically like aggregate the data, right? And it will give the final output. Okay. So in the after the mapper phase, after sort and shuffle, this is how my data looks like. Let's say Apple has 10,000 entries. It will have 10,000 ones here, 10,000 ones here, right? So instead of sending this data directly as is to a reducer, can I do something here so that I reduce the burden of sending all of this data to my reducer? Because A, this is incredibly inefficient, right? Imagine, like sending Apple, comma, the actual count of Apple on single node. Let's say this node has 5,000 entries of Apple, right? On the data that it is produced in the word count example. So I'll send Apple, comma, 5,000 here. This consumes much, 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 much less data. It is just a scalar value. But the list is not scalar value. The list is a vector value. That means it has a lot of entries in it, and you have to say, it consumes a lot of data in Java program, right? So now, since the reducer is doing the aggregation part and getting the final output, can I do locally the same job here and only send this, Apple comma 5,000 instead of, 5,000, entries of ones in a list? Yes, I can do that. So that is where the combiner comes into picture. Combiner is basically a reducer that is running in a map, but there are some limitations to it. Okay. So you can ask me, why are we, what is the problem in sending this one? Okay, I understand that it's a list, but it doesn't harm us sending all of the data, right? Of course it does harm, because since your reducer can be only one reducer or couple of reducers, if we send all of this data, like not just for Apple word, all of this data from across the nodes into one single pore reducer, it runs out of memory on memory means basically RAM on this particular reducer, and then it will crash. Okay. It will crash with a exception or an error called out of memory exception. This is one of the most famous exceptions or errors in all of like Hadoop ecosystem, basically in Spark, in MapReduce, in all sorts of like processing frameworks in Hadoop ecosystem, right? Be careful. Sorry, you have to be very knowledgeable about this one. So out of memory exception happens when a reducer tries to read all of the data from each of these nodes, and it gets overwhelmed with the like number of records, the sheer number of records out of all of these particular nodes that is coming directly into a reducer phase. So it just gives up and says that, okay, I don't have any memory, boss. That's about it. I'm done with my this. I cannot process it, so I'm throwing an error. That error is out of memory exception, right? So that is why we want to do a pre-reduce and then do it. Since we are doing only sum here, right? This is, if you want to give this value to reduce to this value, this is just a sum operation, right? Whether we do it on map phase, whether we do it on reduce phase, the meaning doesn't change. So we are good to go. Okay. So this is why we are introducing a combiner phase. Does combiner phase work all the time? Right? Instead of reducer phase, can we use combiner phase first for every type of operations? No. I'll give an example as to when it can be used and when it cannot be used. So let's say I have four nodes, right? four nodes in my cluster. Okay, four nodes in my cluster. Okay, suppose I want to do a sum here, okay, locally of the word, hello. Okay, finally I got around, 5,000 here. Okay, and in this node, I have hello as 2000. Okay, here it is hello as 3000. Okay, here there is no hello. Here there is no hello. Okay, so even if we add, this is your, map phase. This is the output map phase with combiner. Okay, this is the output of map. Okay, map plus combiner. Okay, this is the output of map plus combiner. Okay, so if I, in the final reducer, when the reduce phase happens, right? When the reduce phase happens, we will get all of these entries. Okay, here. Okay, hello, comma 5,000. Okay, comma 2,000. Okay, 3,000. We'll get everything. When we do the sum again in the reducer here, the final output is, what we are expecting. That is 10,000, right? The final output of the reducer, doesn't change its meaning, right? It's just a sum. Whether I do it in map phase, whether I do it in reduce phase, I'll get the same result. Okay. Same goes with min. Same goes with max. Same goes with distinct. Okay. Whether I do a min or max or distinct here on the map phase, and then again do it again, on final data in the reduce phase, it doesn't change. That's not true with averages. That's not true with averages. Okay. Let's say I've done some average count of hello here and I've gotten 250. Okay. Sorry, 250. Okay. Here I have gotten, 100 here. Okay. Average count. I cannot take those averages and do again an average here. I cannot say, 250 plus, 100 plus, whatever, and then, n divided by n. This is an average formula, right? I cannot do an average here again. Average of averages is a wrong calculation mathematically. So we cannot do that. So that's why this particular reduce phase, should uh, have some operations reserved to it, and that cannot be done in combiners. So that one, the one such operation is your average. Average needs all the values from all of the nodes in one single node. Okay, and then we can, like, literally, do a final aggregation on, or final, average on reduce phase. So can we still use combiner here with averages? Yes. How do we do that? Instead of sending the average directly to reducer, what if we just send sum, comma, number of entries? Okay. Because average ka formula is basically, you know, uh, sum, okay, sum of elements, right? By number of elements, right? Number of elements. So what we can do here is we can send sum, we can send number of elements, okay, 5,000 comma, 300 or something like that, right? And then here at in the final, we can use this. So 5,000, 2,000, 3,000, likewise, 300, 100, 50. These are the number of elements. So 10,000 divided by, this is 50, right? 450. 10,000 divided by 450. So this one is correct, right? This one is correct because we are essentially getting both the count of the word, the sum of the, occurrences, and basically just the words, how many words are there. So that's how it is, right? So there are few other, particular, jobs that requires only map phase, right? Not even reduce phase, only map phase. What are those? If you want to filter out data, you don't need any reduce phase, right? You're not like getting one final output, right? Let's say you have some junk data that you have got, and you want to like maybe remove cuss words or anything like that from your MapReduce inputs. So even before you start processing data for word count problem, what you are basically doing is saying that, okay, let me filter out all of the cuss words or all of the bad words from my input, and then actually start my job of word count processing. So there is no aggregation required, hence no reduce phase required here. And then there is no output. The output of the map phase is the final output phase. Okay. So suppose you have 10,000 entries of sales here. You want to like get only these are entries of sales. This is your order. Okay, order ID, and this is your amount. Okay, and this is order status. Okay, so before you do any calculations on this data, on this tabular data, I want to have only those orders which amount is greater than $10,000. Okay, this is my first phase. Any record that has $10,000 or amount greater than or equal to $10,000, I'm considering only that. So this can parallelly happen in all of the nodes in the cluster, and that can be outputted into one location on HDFS. And our actual job can pick up these values that has the amount column greater than 10,000 $10,000. So that's how it works. Okay. Yeah, that's it, guys. That's it for this session. If you have any doubts, I'll stop the recording now. You can ask away. 1 second. How do I stop recording?